Hi everyone, my name is Diane Roth, and in this presentation I will be talking to you about a project we have been working on with our collaborators at the Southern University of Science and Technology in Shenzhen, and which is about generating color 3D images from planar metasurfaces. So as you may know, there are many different techniques that are now available for the 2D visualization of 3D effects, and these are mainly based on depth cues, which will influence how the brain is processing the visual information it receives and how it perceives depth. So these cues can be classified into different categories. The first one is physiological depth cues, which are simply related to the motion of the eye, essentially. And here are a few examples. The first one is stereopsis, which is related to the fact that each of your eyes are seeing a slightly different image, and this will create a 3D perception. The second example is accommodation and convergence, here again related to the motion of the eye and how the eyes adjust to objects that are close or further away. And this is also used by the brain to interpret distance and depth. The last example is the motion parallax, for instance, which arises from the relative velocities of objects which are moving in front of you. It's like being on a train or in a car, as a close object will appear to be moving faster than an object which is further away. The second category of depth cues are psychological depth cues, and here again are a few examples. So we've got linear perspective, cast shadows and relative sizes between objects, occlusion between objects, and also texture gradient. But the one I will be mostly interested in this presentation is shading and lighting. So if you look at this shape here, there's no reason why you would think it is 3D. However, if I apply shading to the object, you're more likely to think it is a 3D box. And this notion is crucial for 3D perception. So in computer graphics, the shading and lighting of 3D objects is typically achieved using a method which is called normal mapping. And this normal mapping technique is generally used to represent small details in a model, such as bumps, grooves, or any kind of texture, really, without the use of actual real geometry, which would make the 3D rendering process quite heavy. So to do so, they use what is called a normal map, which basically contains the direction of a normal vector at each pixel of the texture, and is then represented as an RGB color pixel, as you can see here for the two bumps that are represented above. So this normal map is then applied onto a coarsely meshed model and is used to modulate how the light reflects off the surface, depending on the angle between the surface normal and the direction of illumination, as well as the direction of observation. So here is a simple example, again, of 3D object and its corresponding normal map. And here is how it would look like compared to the real 3D object. So this is not the most striking example, but it shows you how it is actually used. So what we have been working on in this project is to bring all these computer tricks to real optical systems. And actually, similar shading effects and visualization of 3D objects can be achieved with reflective metasurfaces via the design control of the reflection direction. So metasurfaces are essentially nanostructured metamaterials that are of subwavelength thicknesses. So like metamaterials, here are a few examples of them. They are man-made materials that consist of assemblies of subwavelength meta-atoms and have very highly tunable electromagnetic properties. So metasurfaces have recently been shown to provide an excellent control over the shaping of optical wavefronts via the manipulation of phase and amplitude of light. Here I list a few applications of metasurfaces, which range from beam steering and enhancement of nonlinear effects to focusing and holography. So let's talk in more details about metasurface holography. So holography in general dates from the late 1940s, with big developments in the 60s and the invention of computer-generated holograms, or CGH, and then throughout the decades with the generation of holograms using SLMs. However, there are still many challenges for these traditional holography techniques, which are mainly due to the fact that these techniques are bulky and macro-scale. This is why recently metamaterials, and in particular metasurfaces, have been at the forefront of holography. And compared to conventional holograms, metasurface-based holography has some major advantages. And in part, thanks to the modern nanofabrication techniques, metasurfaces have been shown to provide significantly reduced subwavelength pixel size, an improved spatial resolution, high precision of the reconstructed images, as well as greater field of view compared to the conventional holograms based on spatial light modulators. And through the years, there has been many nice studies looking into the generation of optical holograms using various degrees of freedom. And some people have been using, for instance, polarization multiplexing, whereby using different helicities of circularly polarized light, different holograms can be produced. Some other studies have used nonlinear optical processes or active metasurfaces to generate holograms. Here we will be mostly interested in wavelength multiplexing or full-color metasurface holography, which remains quite challenging at the moment. So wavelength multiplexing has so far mainly been achieved using two different techniques. So the first one is interleaved designs, where the unit cell of the metasurface is not composed of one subwavelength element, but multiple subwavelength elements, which respond to different wavelengths, here red, blue, and green. This obviously degrades the image quality due to the increased pixel size. The second method is off-axis illumination, so it relies on singular subwavelength elements per unit cell, but an off-axis illumination for each of the RGB wavelength, which is not very convenient either for practical applications. In this study, we're working towards designing a metasurfaces that imitates the shading effects of 3D objects using the concept of normal mapping. So we want our metasurface to be broadband, including the main RG and B wavelength. We do not want the metasurface to use interleaved design or off-axis illumination, and we would like it to perform with incoherent light. So as a proof of principle, we have designed a metasurface that imitates the lighting and shading of a 3D cube. So let me now go through how we design such a metasurface, which could be used, for instance, in security features or as engineered optical diffusers. So the practical realization of shading effects with a metasurface is based on a mixed reflection, which essentially combines a specular reflection for the control of the reflection angle, and which is governed by the generalized Snell's law. It is here designed to reflect towards the observer the light incident in the direction of a normal vector of the respective cube face, in analogy to the normal mapping technique that I presented earlier. The second part is a diffuse reflection in order to ensure a smooth change in brightness of the cube faces in response to the variation of the angle of illumination. And here the smooth variation of the shading is provided by the wide angular distribution of the diffuse reflection, which is actually crucial for the realization of this 3D effect. In order to achieve this mixed specular diffuse reflection, the phase distribution of the metasurface requires the combination of a linear phase gradient, shown here in blue, which defines the direction of maximum reflection for each of the cube faces, and a parabolic phase variation, here in red, which provides the diffuse scattering effect. So the combination of this linear phase gradient and parabolic phase variation gives you the curve in white here in the 1D case, and this patch here in the 2D case. The middle image here is the phase distribution of the whole 3D cube sample, which is about 400 by 400 micron. And on the right side here you can see a zoom into the central part of the metasurface phase distribution. And you can see that the pattern is arranged into 2D square patches, which are about 7 by 7 micron, which are periodically repeated. The implementation of the metasurface is based on the Pancharatnam-Berry geometric phase method, where the phase elements are these little aluminium nanorods, which are placed on an aluminium ground plate and separated from it by a dielectric layer of magnesium fluoride. Here, the phase shift imposed onto the light is equal to double the rotation angle of the nanorods with respect to the x-axis. So I remind you the aim of our study was to optimize the structure for the red, green and blue wavelength, and the main challenge we have been facing here was to achieve good performance in the blue spectral region because of the presence of surface plasmon polaritons at the metal dielectric interface, leading into a drop in reflection, as you can see here in this graph. But overall, after optimization, we managed to get an efficiency which was superior to 65% in the range from 450 to 640 nanometers, and that for angle of incidences up to about 30 degrees. Then we went on to fabricating our metasurface. This has been done by our collaborators in China. The metasurface was fabricated using electron beam lithography, and here are the geometrical parameters of the metasurface. So you can see that the nanorods are about 60 nanometers wide, 150 nanometers in length, and about 30 nanometers in height. And the unit cell is about 190 by 190 nanometers. Here is an SEM image of the metasurface, which in total measures about 400 by 400 microns. This is the experimental setup we have been using to characterize our metasurface. The sample is here and is illuminated using a tungsten halogen white light lamp, which is left circularly polarized. The illumination arm can be moved in order to change the angle of incidence onto the sample. The light is slightly focused onto the sample, and we look at our metasurface, or at the image generated by the metasurface at normal incidence from it, using either a CCD camera or a spectrometer, depending on the measurement. And here you can see the image generated by our metasurface, which indeed contains signal into the 3 red, green and blue channels of our camera, which we calibrated first using white office paper and made sure we got equal signal into the 3 channels. However, you can still see that the metasurface shows a slight blue-green hue, and this is due to the fact that the metasurface was optimized for a wavelength of 532 nanometers. It is possible eventually to improve that using a mixed set of phase patches, which would be designed for 2 or 3 different wavelengths. So now we look at the dependence of the generated image on the angle of incidence onto the sample, and from this series of images you can see that we get a pretty similar efficiency for angles of incidence up to about 30 or 35 degrees. And then the image gets redder and redder. So this result has been summarized in this graph of diffraction efficiency here, that we obtained by integrating the intensity in this bright face of the cube for each of the images. And you can see the blue and green efficiency quite high for low angles of incidence and decreasing significantly for high angles of incidence. And this is in agreement with our theoretical predictions that we obtained from the discrete Fourier transform of the phase distribution that I showed you earlier in the previous slides. Here we look at the dependence of the generated image on the angle of rotation of the sample to check that we get a realistic 3D effect. And indeed we see a smooth change in brightness in response to the variation of illumination angles. Here, as you can see, the bright face of the cube is always facing the illumination. So the last experiment we did here was to try to add 3D perception to pre-existing 2D images, and to do so we printed this cube checker pattern onto this transparent slide, as you can see in this middle image. Here you can see the cube for different angles of rotation, where of course you don't see any 3D effect. And then we placed this film onto our metasurface to regain the 3D perception, and as you can see from the bottom row here. So the contrast in these images is a bit worse than the other images you've seen, and this is due to the scattering of the film in the darker region here. So before I conclude, I wanted to emphasize the fact that this setup can also be very simple and practical. While the results we presented earlier were recorded using a tungsten halogen white light lamp as well as lab-grade polarizers, this setup also works using a simple white LED and the polarizing filters of your standard 3D cinema glasses, for instance. This setup is also very flexible in terms of angles of incidence and observation. And here are a few images that we took with this much simpler setup, and as you can see we get very nice results too. And in terms of outlook for this project, we're currently looking into fabricating these sort of metasurfaces onto flexible substrates, which would then be interesting for anti-counterfeiting applications, for instance. As a conclusion, we have designed a color metasurface structure that performs the shading and lighting of 3D objects. Our design shows broadband performance, including the main RGB wavelength, and works under incoherent illumination. We are now working on fabricating these metasurfaces on flexible substrates, and this could be interesting in applications related to 3D security features for anti-counterfeiting, or in areas where engineered diffuse materials are used. Finally, I would like to thank our funding bodies, our collaborators in Shenzhen, and thank you very much for listening. If you have any questions, please feel free to contact me on Twitter or via email.